In this video here, we're going to be talking about radioactive decay. And this one, I'm just going to go through the formula for radioactive decay and explain what all the parts of the formula mean. And then I'll do another video where I actually go through an example problem. Most of the problems that involve this type of stuff are multiple steps, so that takes a lot of time. So I'll just do a separate video where we go through an example. This one, I'll just explain the formula. Now, if you watch the video that I did on exponential growth and like population growth, the formula for radioactive decay is very similar to the formula for exponential growth and population growth. Really, the only difference is they use the letter M instead of the letter N. And then for population growth, the exponent is positive. For radioactive decay, the exponent is negative. Other than that, it's basically the same exact formula. All right, so the formula for radioactive decay, M of t is equal to m sub 0 e to the negative RT. All right, and again, if you saw the video on exponential growth, that should look pretty familiar, right? And if you didn't see that video, you should check it out because it's another application of exponential functions is using it for exponential growth and population growth. All right, so first off, before we even get into what all this stuff represents, well, let me tell you what all this stuff represents, and then I'll explain what radioactive decay is really all about. All right, so M of t is the amount present at time t, right? So you have a radioactive substance. However much of that radioactive substance you have at time t, that's your M of t, right? M sub 0 is the initial amount of the radioactive substance at time t equals 0. If you think about it, if I plug in t equals 0, well, 0 times whatever r is going to equal 0. So I'm going to have e to the 0 power. Anything to the 0 power equals 1. So I end up with m sub 0 times 1. So my amount that's present at time t equals 0, when I plug in a 0 for t, equals that m sub 0. Because it just becomes m sub 0 times 1. And so that m sub 0 is always going to be my initial amount of whatever it is. When we're doing population growth, the n sub 0 that was in front was the initial population that we were talking about. Now that we're doing radioactive decay, that m sub 0 is the initial amount of radioactive substance. All right, when you're doing modeling with exponential functions, that number in front of the e is always going to be your initial amount, right? The beginning amount. All right, so that's my m sub 0. The r is the relative decay rate, right? The rate at which our radioactive substance is decaying over time. Now, there's a formula to calculate r. Some problems will tell you what r is, right? It's decaying at 32%, so r equals 0.32. Some problems will tell you the half-life of the radioactive substance. The half-life, we give that the letter h for half-life, and then the formula is that the relative decay rate equals the natural log of 2 divided by h, divided by that half-life, right? And then t, of course, represents time, and you can use any units of time. Sometimes for some radioactive substances, time is measured in hours. For some of them, it's days. For some of them, it's years. So you can use any period of time as long as you're consistent throughout the problem. If t is years in the beginning, then every number you plug in for t has to be in years as you work with that equation. All right, now, back to this stuff with the half-life and the relative decay rate. All right, so how radioactive substances work. You got a radioactive substance, right? Some chunk of metal or something that's radioactive. All right, what makes it radioactive is, and I'm not a physicist, so I'm going to explain this to the best of my ability, to the best of my knowledge. The radioactive substances, their atoms have like extra particles in the nucleus of the atom, and every once in a while one of those particles will just kind of leave the nucleus and like zoom out and release energy when it does that, and that energy that it releases as it leaves the nucleus is the radioactivity. We call that radioactivity, right? So for each atom of this radioactive substance, we have no idea exactly when any single atom is going to get rid of its extra particles and release its radioactivity. Like, we don't know exactly when that's going to happen, but statistically speaking, over a long enough period of time, it happens in a consistent manner, right? And that manner is what we call the half-life. So let's say I have 100 pounds of some radioactive substance, and let's say the half-life of that substance is 5 years, just to pick some easy numbers here. So I've got 100 pounds of this radioactive substance, and the half-life is 5 years. So that means over 5 years of time, half of those atoms are going to lose their radioactive particles, and so after 5 years, only 50 pounds of that stuff is still going to be radioactive. Half of it is no longer radioactive because it lost its isotopes or whatever they're called, and so only half of it is still radioactive. After another 5 years, half of that was remaining is still going to be radioactive. So if we start with 100 pounds, after 5 years, only 50 pounds are still radioactive. After another 5 years, now only 25 pounds are still radioactive. So every half-life, right, every 5 years in this case that go by, half of this radioactive substance is losing its radioactivity, and only half of it remains radioactive. Right? So after another 5 years, it would be down to 12.5 pounds of the radioactive substance. Right? That's what we mean by half-life. So if we know the half-life, we can plug it into this formula to figure out our relative decay rate, and then use that number in our formula up here. Right? So for radioactive decay, there's like an extra formula you have to know besides just the general model for radioactive decay. All right? And like I said, when these substances are losing their atoms, like you can't predict when any single atom is going to lose its isotopes or its particles and release its radioactivity, but we know that over 5 years, half of them will do that. It does statistically follow that consistent pattern, so you can predict in bulk how much of it is going to still be radioactive after a certain amount of time, and that's what this formula here is going to do. All right, so that's, for what it's worth, that's my understanding of how radioactivity works. I'm pretty sure it's fairly accurate. I may not have covered every single part of it. Obviously, I'm sure radioactivity is a much deeper subject than what I just talked about in 2 minutes. But I don't think I said anything that's necessarily incorrect about it. Hopefully it makes. Right, so that's the formula. That's what we need for radioactive decay. So make sure you check out the next video that I'm about to do, where I'll actually go through an example of writing a radioactive decay equation and then using that to solve some problems involving the radioactive decay.